Here's a problem I want to do with you. That is problem 13.3 of the book. And this problem has a little bit of everything in it. So I'm going to erase the board here to start working on it. In this problem, you have a radiant cavity. I have no idea what the application for this would be, but that's okay. It's a good enough problem for now. So in this radiant cavity, you have these cylinders, 1, 2, 3, like annular, like pieces of pipe, and a bottom. They drew only this one here, but each of these ones has an electrical heater inside, right? So we would have 1, 2, 3, 4 heaters. And it is divided in 4. Typically, in this type of applications, you would have a control system that keeps them at the right temperature. And you want all of them to be at the same temperature. So you want them all to be at 1650 degrees C. Right? You want all of them at 1650 degrees. But the outside, this little hole, is connected to a surroundings that is essentially room temperature, right? 300 Kelvin. The question here is, if I want this to be at 1650 degrees, and this is open to 300 Kelvin, and I have this electrical heater, how much heat, right? How much power should I put in each of these elements, right? So how much power do I need to put? And this, let's forget about convection, let's forget about everything. This is just pure radiation issue, right? You didn't know how to solve this problem. You couldn't have solved it before because we need to use view factors in this case. So we are going to assume for this problem that is a black body heat exchange, right? And when we see that something is 1650, it would be some kind of a refractory ceramic. Those things, if you remember the table, the values we saw before, it's 0.9 or 1, something like that, close enough to a black body. I like the math of the black body then. So let's start doing it. And I'm going to start by calculating how much heat I need to put in this bottom element. If we have time, we're going to calculate how much heat we need in this other element here. So let's get started. So although the book didn't do it, here we have a resistor, another one. And this is a schematic because in reality the resistor would go like be wrapped around it. And I'm going to call this surface 1, this surface 2, this other one surface 3, this other one surface 4. We have the surroundings here. (300 Kelvin), and we have that each of these surfaces, right? All right, let's put some dimensions here. This is, and this is split in 3 equal parts, and here we have R equals. All right. So we can start working on it now. Okay, good point. So you mentioned thermal conductivity, and I'm going to say that this is insulated in an adiabatic way here. So thank you for bringing that up. I was forgetting to say that this is insulated. Emissivity is 1. Of course, things are not perfect 1. But we're going to claim it's 1, and just, you need to know that it's near 0.9. But we're going to say it's 1, right? And forget about all the other problems we would have with subtleties. So, all right. So let's do, consider element 1, right? And the question is, how much electrical power do I need to put in there? So I just for the sake of good old times, I would say Q in minus Q out plus Q generated equals Q stored. So what we always do, we start like taking some things out. Can I take anything out here? So Q in is not happening. Okay, I'd like to take another one out. Eventually it's going to be steady state. And nobody said anything about times or anything else. So we're going to assume it's in steady state. And there are good reasons to believe this would go into steady state quite quickly. Right? Is that what you had in mind? Okay. All right. So look at this. We have these two guys. What can you tell me about these? What heat transfer mechanism we have for Q out? Yeah, better be radiation, right? That's the whole point of what we're talking about. And I said conveniently, let's forget about convection or conduction or anything else. Right? This is Q radiation. Okay. Q gen. Is Q gen 0? What is it? Right. No, Q gen in this case cannot be 0. Otherwise, we have a real problem. And this is the heat that is generated internally. And nobody called me on this. Nobody called me. But I made a... I violated one of my own laws, right? We cannot write a balance without a... But you see, I already passed my class. I'm safe. But you always have to do that. I forgot, right? You have to do this balance, right? So internally, you're generating heat. If you take each of these elements individually, you have this internal heat generation in this case. The question of the problem is, what is Q gen, right? And you're going to say Q gen is Q radiation. Kind of trivial. Many of you would, the book jumps straight into calculating radiation. But if you now were to say, you know what? I don't like it insulated anymore. I would say, no problem, because we have that balance. We can deal with that. We can do anything we want. Right? So this is very, very powerful, even if it looks simple. So let's consider element 1, right? And the way we're going to do this is this loses energy. Does element 1 loses energy to element 2 or gain? No, same temperature. 2, 3, and 4, same story. We're losing energy to the top, right? What's the shape of the top? So we don't know. So you're actually anticipating something. That is what we're going to do. We're going to put a virtual surface here. Because we don't know what is out there. But we know this awesome virtual surface trick that says, whatever you had out there, you could have Mickey Mouse looking at it from outside. You don't care anymore. Because you put this virtual surface. Virtual surface that I think we called 5. Let's call it A5. All right? So, first step, quite okay. Energy losses, right? So we have Q1 is Q1 to 1. All right, let's go. Surface 1. Does it have a self view? No, surface 1 is flat. Right, so no point here sees any other point. Right, so it's flat. This is 0. 1, 3, 2, 3, and 4. Do we have heat exchange between 1 and 2, 1, 3, and 1, 4? No, we have already said it a million times. And the reason is because they have the same temperature. Now, again, we're being methodical so we can tackle difficult problems. In the end, Q1 is Q15, right? And how we do Q15? All right, Q15 is A1 times F15. Right, no epsilon, but yes, view factor. You couldn't have done this before because you'd have forgotten about this F15. And you're going to see F15 actually is pretty small. because it sees only a little tiny hole at the end. So times sigma times T1 to the 4 minus T1 to the T5 to the 4. And of course, it's in Kelvin, right? What we're doing is very advanced. Doesn't look like, because its formula is the same you had before. Instead of saying, oh, I have epsilon, now you say, I have the A1, you even knew it too. You have this view factor. So we have A1 is pi r squared, that is 1.96 times 10 to the minus 3 meters square. Right? This is it. That's A1. So, and to be clear, the surface we're talking about, we see it only from one end, right? So, sigma is 5.67 times 10 to the minus 8 watts per meter square Kelvin, fourth. Now, F15. So what we do is similar to convection. We go to our tables and we look what has a similar geometry. Which of these three? Middle one, right? Two circles. And in this case, it's simple because the two circles are the same, but we could have done a cone. We can do crazy stuff, no problem. So this is a look at table 13.2 for coaxial. And there's a guy in the internet who's been collecting these view factors all his life. And if you go, I should bring you the link. I don't remember off the top of my head. You say what you want, and somebody, whoever did the quadruple integral, he has it on the website. Much more than here in we have on the board. Coaxial parallel disks, right? And says F. I'm going to do it with so you need to do S and you need to do this little r. And S is 1 plus R5 square over R1 square. Beautiful. And now I know better. The book is not inconsistent with the notation. Big R is not a mistake. Big R is R5 over L. Or it would be, or this would be R5, right? And R1 is the same, right? The radius is the same because it's a cylinder. And this equals R1, 2 is 0.167. And then I can calculate S, and S is 38. And now I can go to F, and sorry, I should put F15 here. And F15 here is 0.0263. Until now you would have said F was 1. The calculations we were doing all the time so far were assuming that F was 1. Right? You would put a sig, an epsilon, whatever, epsilon of 0.9, fine. But you were assuming, you and me, as of today, that F was 1. Wow, you'd be seriously off. You'd be off by a factor of 50 or something like that, 40, right? And this is the right calculation. So now, once we calculated that, I can say Q1 equals Q15 equals A1 F15 sigma T1 to the 4th minus T5 to the 4th equals 39.9 watts. This is advanced. And very simple, because we have the tables. What happened to the rest of radiation? Okay, good question. this is giving radiation out there, but this is also giving radiation to this guy here, right? Yes, and this is giving just as much radiation back because you're at the same temperature. So that's what's happening. So this is radiating all over the place and getting from all over the place. But these exchanges are neutral, net neutral. This is not. Very briefly, I want to sketch for you how to do Q2. Very different. So that's an element 2 now. So we would do the same energy balance. And so we know that Q2 would be Q25, right? Do we agree with that? It's with the surface because everything else is at the same temperature. Now I have a problem. This is a cylinder that sees this guy here, sees this other guy here, sees this, sees outside, sees itself. Big problem. Now, big problem which we can solve because what we can do instead is, instead of seeing what this guy gives to other one to the other area, we can do another virtual surface here. And here's where things become kind of brain teasers. The book calls this A double prime for whatever reason, right? Now look at this. We know that 1 to 5, 2 to 5, and 5 to 2 are more or less the same, except in the areas. So I'm going to look, instead of 2 to 5, I'm going to look instead of 2 to 5, we look 5 to 2. And if we do 5 to 2, is we would say 5 to 2 and 5 to 1 is the same as 5 to this A double prime, right? So, and so we would have 5 f of 5 to A double prime is f52 plus f51. This is the one we care about. Now, this is the additive property. Right, and so we could say f52 equals f5 A double prime minus f51. And f25, that is the one we want, that is a5 over a2 f52. This is reciprocity. Now look at this. f5 to a double prime is the two circles, right, connecting with each other. This one, we know. 2 circles. Now, f51 is the same as f15 because the areas are the same. 1 and 5 have the same area, right? Bottom line, this was easy to calculate. This one you already knew. You take these two and you get the f52 that it was the difficult one. This is way beyond just your intuition. Look, here's where we are. Just as a brief recap. We spent, I'm stealing this slide from Ying. That made it so pretty and I ruined it last time. So we started with energy balances, then we looked at heat transfer mechanisms in a very simple way. We did conduction, then we did convection, phase change, heat exchangers, radiation. We did so much. So if any of you is interested in some of these things, the next step of what we've been doing this, I teach welding. I'm not a welder, I don't know how to weld, but I like many of the physics involved. So we'll be teaching a class. It's 481 for undergrads. Next semester that you can come, and let me tell you some cool things like this. That's thermal image of welding. There is so much to be said about that. But the really interesting thing that I think you would have an appreciation for, you see all those formulas? Remember when I tell you about the poor souls spending years? All right. That's how that's Ying in doing those things. So we have not discussed in this class about moving heat sources, like when you move a heat source. But there's a whole bunch of things that would be used just like we do. Please don't forget to fill in your class evaluations, especially if you like the class. This is it. Thank you very much.